So the work started in collaboration with a team from America, David Macmillan. I'm very sorry. I don't know if somebody has some water. So we started a project on copper complexes with David Macmillan, as I said. And David Macmillan spent a year in Strasbourg. He was on sabbatical leave. And we had made the molecule which is represented here, a very simple molecule. David Macmillan was more of a physicist than a chemist. He was a photophysicist. And he was very excited when he saw the molecule. And he said, we must collaborate. And we started a collaboration immediately. So we started from this molecule, very simple molecule. We mixed with copper 1 plus, copper tetrakis acetonitrile, and very, very easily we obtain a copper complex. This molecule on the right, I don't know if you see my laser, but I don't think you see anything, do you? Yeah? Personally, I do not see it. So the copper complex, which is here, was very exciting in terms of photochemistry, but there was something else. And now we will try to discover the something else together. If you imagine that you link the point, very difficult, a point which is above here to another point, let me try. So the idea is quite simple, but it's very difficult to explain without a laser. You can make a ring in a vertical plane. You can make another ring in a horizontal plane. And those two rings will be interlocking with one another. Yeah? Microphone, yes, sorry. So you can make a ring in a vertical plane, another ring in a horizontal plane, and those two rings will be interlocking with one another. So you will see immediately how it works. So we had to decide, shall we be photochemists and stay photochemists or photophysicists, or move to another field, and we decided to jump to another field, which was that of catenanes and rotaxanes. Within a couple of months, we had our first publication, thanks to the talent of Christian Dietrich Büchecker, a great organic chemist, great synthetic chemist. And we published our first paper in 1983. Just a couple of months of work. It was published in French. Be careful, it's published in French. In a reasonably good journal, but not a high-impact journal. But the main reason is that high-impact journals didn't mean anything to us at the time. So this is a video which shows you how it works. So we start from the molecule, which is here, and we will mix it with copper, and we obtain some kind of N-twine complex. We make a ring on the right, another ring on the left, and here we are. Thank you. Thank you very much. Thank you. And here we are. We have our catenane. And so we developed another strategy which is slightly more complex. We made a ring, which is here, and now we will proceed to threading of the ring by another fragment, organic fragment, thanks to the effect of copper. Copper arrives, it forces the second fragment to thread in, and then we cyclize. So that was the very beginning of catenanes. I should say that all of a sudden, catenanes appeared as very accessible molecules. It was a three-step synthesis. The yield was really good, and we could make such molecules at the gram scale. So here are structures. This is the copper-containing species. We can easily remove the copper, and we obtain the metal-free species, which shows that the system has completely rearranged. I should say in passing that we have been very much interested in molecular topology for years and years, and we have probably devoted as much effort in the field of topology as in the field of molecular machines. And we could make quite exotic topologies, very complex topologies, such as the trefoil knot, which is on the left here, or Solomon, the Solomon link, which is on the right, and other more complex topologies. And these molecules have really fantastic properties. But it's not the subject of today's lecture. Just to show you that knots and catenanes are everywhere, in DNA, in proteins, in viruses. And so we thought it was also a motivation for us to show that chemists can make complex topologies in a way not really similar, but reminiscent of what nature can do, knots with DNA, knots with proteins and viruses. On proteins, just one point. If you look at the crystal data bank in Cambridge, 1 and 2% of the proteins which have been crystallographically fully characterized are knotted. So knots are everywhere in any living organism. Now let's look at the first molecular machine we made in Strasbourg. It is built on a catenane. So this is very simple coordination chemistry now. We will start from here, on the left, the upper line, and we have copper 1 as the metal. Copper 1 plus is not really a transition metal. It's a D10 electronic configuration metal, and it is very happy if it is surrounded by 4 nitrogen atoms, as indicated here. And now we will oxidize, abstract an electron from copper 1 to generate copper 2. This is on the right part of the upper line. Copper 2 plus is now a real transition metal, and it wants to be 5 coordinated. So the ring, which is here, will move, will rotate, and the 3 nitrogen atoms, which were originally at the periphery, will replace the 2 nitrogen atoms originally interacting with copper, so as to generate the new species, which is on the right at the bottom line. So this is a half turn. We can go back, we reduce copper 2 to copper 1, we generate a very unstable species, which will rearrange. Again, the ring will glide, and we will regenerate the starting form of the molecule. So that was really the beginning, and it works beautifully. It's very, very clean. We never detected any degradation, any fatigue of the system.